Sorry. Now it's done. Thank you. So many people that are not from the discipline think that big data is data processing and data analytics. It is part of big data, but this doesn't mean big data. And so they associate with applying artificial intelligence algorithms and analytics and data preparation, data engineering, etc., which is part of big data processing, but big data processing is much more than just applying algorithms and tuning the parameters in order to drive models. So that's part of it, but it's not all of it. And well, we have devoted some weeks reasoning about data management, the storage, data fragmentation, which is the back end of the summit of the iceberg, which would be then being able to analyze and define data processing pipelines in order to drive models. But anyway, we are also going to see some examples of this aspect of big data, and so we're starting today. Just a second. So I will try to not to speak a lot so that we really go into the matter rather than blah blah. Okay. So everything starts from the fact that, in fact, what we know as querying is, again, just a little part of what it is possible to do when we query data collections. So for the time being, what we have seen is NoSQL-like querying, which is really related as an alternative to the relational approach, where you have data more or less structured and you define operations in order to explore your data. And these operators change depending on the underlying data model and the underlying data structures that you have stored. Yet there are other queries that cannot be answered using this type of approach. There are two big families of such kind of queries. First of all, I'm going to start from the bottom to the top. First of all, queries that refer to classification questions, okay? For example, given a set of images of steel sheets, identify those that have wounds in the central area. Which are the characteristics of clients willing to buy electric vehicles? Which anomalies cause fatal breakdown in machines? Okay, so these are examples of classification queries that cannot be addressed with the querying approach that we have studied until now. The second family would be prediction queries, which is, for example, the expected evolution of the market of electric vehicles. So out of a set of observations, try to predict what will happen with respect to this market. Or the expected active life of a manufacturing machine before its first breakdown. And these type of queries are important because they are related in many of the times to decision making. And when we started this course and the lab, we said that we are interested in providing solutions where decision making is based on data. Okay? So once we have seen the different models and data that we can have, now come the queries, okay? Which are these decision-making queries that are so particular and that cannot be answered with classic approaches, okay? So this is what we are stepping in for the first time in the lecture today. So in fact, the difference between the type of queries that we know and these new families of queries is that they call for experimental data processing approaches. Again, when we introduced the lab, we said, okay, in fact, what happens is that there are many experimental sciences that ask this type of queries, and they have to use the data in order to drive experiments that will lead, into some kind of answer. Okay, and first question is, of course, identifying the type of queries that concern this experimental approach and what are the type of results that we expect when we answer this type of queries. And is today related to big data. In fact, the evolution of the big data trend has landed into a science known as data science. Okay, so normally today, as I said in the introduction of the lab, I mean, of course, the majority of people tend to talk about big data, but in fact, today, what we address is data science problems, okay? Because we have seen that the methodology required in order to deal with this type of questions on top of the data collections that we have described out of the 5B model call for a new scientific methodology that can be used in order to address these problems. So just to make sure that we are on the same page, data science is the representation of complex environments by rich data opens the possibility of applying scientific knowledge regarding how to infer knowledge from data. Okay, so the object of study of this science is, of course, data, but the question that it answers is how to infer knowledge from data. And so it is a methodology, as any science, that is proposes actionable insights that can be inferred from data. And what is the particularity with respect to other related disciplines? Related disciplines, in the good old times, we talked about data mining, artificial intelligence, which is part of a tool used by data science in its many different forms, data management, data querying. So these different disciplines come together in this methodology provided and proposed by data science. So it has multiple facets, and that include not only, I mean, computer science and algorithmic aspects, but also it includes business, it includes, of course, big data, data engineering, data governance, so a lot of disciplines that come together in order to feed the methodology proposed by data science. And of course, the objective is produce beliefs informed by data and to be used as the basis of decision making. In the absence of data, beliefs are uninformed and decisions are based on best practices and intuition. And this is not good. If you are a company or an organization, this is not good, but because if your human assets of course, they gather knowledge of the processes, etc., in their minds, and they never report this and define a clear methodology of this. If they leave the company, they leave with the knowledge of your company. Okay, so the idea is rather than this, and of course, if the problems of your company are too complex, every human asset will have different perspectives of the problem. And fragmentation of perspective means that at some point there are aspects of the problem that you are missing. And this is really critical. Example of this, we have seen the pandemic. Many disciplines, biology, virology, different disciplines in medicine have different perspectives of the virus and of the disease, and this has made it very complicated, almost 2 years, to figure out and how does the disease and the virus works in order to develop some medical, biological, etc. strategies. Okay. So this is because we were uninformed, because it didn't exist. So the idea is that you gather data, etc., and such that your decisions will be based on this. And of course, this you have to maintain, because some data, new data come, new observations come, new conclusions come, etc. And out of experience, since it is an experimental science, you will develop much more knowledge. In fact, when we deal with data science queries, in fact, we are dealing with four types of questions. First question is, if you given a phenomenon, you want to understand what happened. Okay. So you get a set of observations and you say what happened. The other type of question is, why did it happen? You go further in your knowledge and you want to ask what will happen. And once you have a lot of knowledge gathered and produced, how can we make it happen? Okay. And related to these four types of questions, you will have different examples of tools, theoretical and technological tools that will help you drive solutions to these questions. For example, when we want to know what happened, tools like descriptive analytics will be very useful in order to understand observations, for example. And there you have that a big bunch of big data processing problems are solved with statistics and probability. So you need solid basis on these aspects of mathematics so that you can develop your experiments and your answer strategies. Then, for example, why did it happen? There is diagnostic analytics with many different algorithms that can help you solve these kind of questions. What will happen? You have predictive analytics. So I don't know if you remember well your statistics courses, but there is inference statistics, for example, that can be applied. Linear regression, I don't know if you're acquainted with it, but okay, these mathematical tools are useful in order to do prediction. Yet mathematical tools are always very rigorous. They ask for the data to have particular mathematical properties. The problem is that observations, when we talk about that data science, they come in a very highly raw status. And when you have raw status of data, the mathematical properties are in general not respected. And so this is why machine learning and artificial intelligence come with a set of algorithmic solutions that get rid of these constraints regarding the data, the properties of the data that you can use to feed a mathematical model. So these alternatives open possibility to answer questions where your data are not ideally organized and the content is not ideally prepared. And then, for example, for answering how can I make it happen, then there is prescriptive analytics with other mathematical and artificial intelligence techniques that can be used in order to answer such type of questions. So we were skiing on the predefined roads, and that was nice because we have everything controlled. And now once we move to this new type of questions, we are out of the road, okay? And there we have to develop for every specific problem and every specific data collection, we have to develop a solution in order to answer your query. It is like if you have to invent the right operators and the right execution plan for a given relational or NoSQL query in order to answer it. Okay, so you do not have operators, anything, and you invent the method that will lead to a possible answer. Okay, so this is what changes from the very controlled context of what we have known regarding query. So the data science has a workflow that is the one that we are going to apply now that we are going to address these problems. So the idea is that every activity of the workflow is a problem itself. Okay, so the first problem is data collection. Okay, which are the methodologies that we are going to apply in order to collect data? Are we setting a set of sensors? Are we setting cameras? Are we using intelligent devices in order to monitor a piece of reality, or as a community of people or a community of entities within a context, so to collect the data? And for example, if you think about cameras in smart cities, how many cameras are you going to install along an avenue, for example, in order to observe the traffic? Every kilometer, every street, where in the street. So you see this setting that will lead to data collection where data will be representative of what you want to observe is a problem itself. Then once you collect and harvest the data, another problem is understand what the content. Okay, so there are many visualization techniques in order to observe the content of the data, depending, of course, on the format and the structure, etc., of the data. Then, as I insisted a lot, that normally when you collect data in such conditions, data are not clean. So you have to clean, and you have eventually to transform, etc., in order that you end up with a representative clean collection that you can use in order to go further in analysis. Then you can drive models, for example, artificial intelligence models or machine learning models that you already know, and then you validate the conclusions. Eventually, you can explore visually the results. Eventually, you can go back to the model or to the cleaning process in order to calibrate and adjust these results. And at some point, you communicate with the ones that will consume the results and that are experts on the problem you are addressing. And when everyone agrees with that, and that they understand the results, then eventually you can deploy the solution. So this is the general workflow of data science. And now today, since there is the cloud, particularly because there is the cloud, and there is also huge movement in order to democratize the access both to data collections and to algorithms, that it is possible to run experiments in a very smoothly manner. Okay, so thanks to these externalized environments that provide us with resources, with transparent management of such resources and at different levels, etc., it is more or less simple, as simple as computing, as when we program. Okay, so, but anyway, it's simple to have access to environments that will help us run the experiments and provide solutions in order to answer these new type of questions that that are new, at least I suppose, for you until now. So it is important that you consider that at least in this chapter, practical chapter that we are opening and where we will stay for some weeks, we are going to normally we are going to combine, of course, mathematics and statistics, machine learning a lot, because my examples will regard machine learning algorithms because they are representative of greedy algorithms that have problems to deal with data and that provide all the difficulty that makes it pertinent and interesting to access cloud computing solutions. Then we will certainly, but not a lot, do a lot of computer science in the sense of algorithmic, yes, and preparation of the environment. At some point, this is why we're going to virtualize and learn how to virtualize in order to have the right environments to run these greedy processes. And that's all, okay? So if you are professionally addressing these kind of problems, you would need, of course, software development strategies, and also business knowledge, because when you deploy, since you are deploying a solution, you have seen that resources have a cost, etc. So you have to develop a business plan that will make it possible for your solution to be used in a generalized and global manner. I think that you are having now a course on strategies for dealing with computing resources in companies. No, I believe you have such kind of course. So the type of decisions that you make in order to buy servers, blah, 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 well, there you would include this part of the reason. No, you're not. I saw, in fact, I saw the program and I saw that you have a kind of course on like management of computing computing centers, no? Don't you? Or I'm just dreaming, maybe. Do you have something like that?
First, doctor, did you say?
There is I saw in the program a course like managing computing centers or something like that. That I believe that it's if you are a CIO of a computing center, how do you make decisions on which servers to buy, how to implement the site, etc. This kind of decision making that a CIO would do. Well, I mean, of course, not maybe not a data center, but for example, the IT center at lab. Now you are the CIO, and how are you going to manage all this? No, it's not Professor Watson who is teaching this.
I don't know. Maybe you're talking about. We took a course called Advanced Databases. I don't know if you're talking about that, where we saw, for example, data warehouses.
No, 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 no. I'm really meaning management.
Oh, okay. I think Well, I think we did not take.
No, okay,
um,
okay.
Yeah.
So, and you are not now.
No, well, no. I think that the only
Oh,
class will be yours of like storage
okay,
and platform.
okay. Yes, because I mean, my the course of Dr. Watson is more about project what? I have the second, it's more about, okay, it's project management, nothing to do with data center management. No. Okay, no problem. So anyway, when I studied at UDLAB like three centuries ago, we had a course where they told you, you know, how to prepare physically the space where with climatization, the right temperature, etc. How do you prevent people to go into the close to the servers, you duplicate it, and blah 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 blah, all that. Okay, so if you have this type of decision, then you also have to consider once, because these are processes that you are going to deploy, okay, and that are very costly. So they might create overhead in the service that you provide as data center to other users. So you have to make sure that you have the right business model such that someone that uses your data center do not, I mean, for your data center, it is not painful to drive this kind of processes. And if it is, you are going to ask for more money, which is what the cloud does, cloud providers. So that would be an enormous topic to consider. Myself, I wouldn't have the enough knowledge to do that because I work in academia, and in academia I have worked with providers, I mean with Microsoft, etc. But since I am academia, I get grants. So I do not have to reason about these kind of limitations that a real company would have in order to deal with budget, etc. So that we are not touching. Okay, so we are having computer science, machine learning, maths, and all together within data science. We are not also touching software development because I will not ask you, this would be too much. I will not ask you to provide finalized prototypes. Okay, we are just having examples of the inner aspect of what we grab into a complete application. That's something that you have done before in other courses. So regarding the famous machine learning, so this part, just to make clear that this would be what, do you know Glassdoor? Do you know what Glassdoor is?
Yes.
Okay, so in an interview, a technical interview for a data science position, you would have to be sure that you master this table of algorithms in order to answer the questions that I have introduced at the beginning and that you would implement into data science solutions. Okay, so it's huge. Yes, yes. So we will just have some pieces of it. Just be acquainted. I mean, be aware that we are really touching the very general aspect of the thing, and there is a world behind. Okay, so but anyway, at least what it is important at the end of this chapter is that you will identify the different families: regression, Bayesian networks, deep learning. For example, Dr. Watson is a specialist in Bayesian networks, deep learning, ensemble, decision trees, etc., so that you identify the families and at least one algorithm or two, the most popular ones of each family. Okay, this would be the very fundamental knowledge that you have to get acquainted with on a general course as ours. Okay. So that's for expectations. Now, just to have the map of the famous querying approaches, and suddenly we have opened the Pandora box, and there are new new queries now. So, in fact, you have two big families. You have the databases and information retrieval family, and you have the data science family of querying approaches. Okay, and if we zoom into these families, you can use 4 criteria in order to classify and profile these families. First of all, of course, we have to identify the types of queries. Okay, then the underlying execution model that we use in order to implement the queries, the properties of the results of the queries, and the kind of data set that we use in order to run the queries. And so in the databases and information retrieval family, the query types are relational, are multidimensional, they can be spatiotemporal, they can have aggregations. You can ask for patterns, as we saw during the course for Neo4j. You can have regular expressions, okay, again, as we saw both in documents and in Neo4j. So that's the type of queries that you can ask when you are on the side of databases. Then on the side of information retrieval that we are used to do is disjunctive and conjunctive queries, as the ones that we asked on Google or in other search engine, and they can be also navigational. I believe that you studied Xquery. Xquery is navigational. Now, with respect to the execution model of your queries, you can have on-demand queries, like the ones we ask on NoSQL and relational databases, or continuous. For example, if we subscribe to an RSS, or if we follow the traffic on Google or our iWatch, etc., we are asking continuous queries, okay? So these are queries where the result changes a long time. Okay? And in information retrieval, normally is on demand. Then with respect to the results properties, normally in the database domain, that's something that we discussed in the course, there is a notion of completeness. Okay? So you obtain complete results, complete with respect to what is stored in the database. And it can be full completeness if we are, for example, in the relational case, and some NoSQL stores have partial completeness. And you can have also fuzziness. There are strategies where they are called fuzzy queries, and you have fuzzy answers. And then with respect to information retrieval, the main difference is that there is approximation, and this is why you have precision and recall and probabilistic tags in order to determine the value of your query. So that in information retrieval we are used. Well, normally the precision and the recall is not exposed directly, but normally what happens is that we know that those that are more relevant, which is a ratio between precision and recall, will come to the top of the result of the search engine, modulo plus probabilistic and economical issues, because if you pay more, your site will appear on the top, and otherwise it goes down onto the second page. And then with respect to data content, in databases, and particularly in relational databases, data are represented in intention. This is why we have a schema, or partially in intention when we have no SQL solutions. And then in information retrieval, you have in extension. Okay, so what you have is a quantitative representation of the data. You have had information retrieval. You have had this course where you have this matrix, the frequency matrix, where you can have either you can use frequency or you can use probability, in order to represent the content of the documents, and you respect the Loon distribution in order to decide which are the relevant topics with respect to a document. So this is in extension, because even if you have a quantitative representation of the data, you have matrices that are used in order to answer our queries. Remember to ask me if you suddenly say that you have learned something that you didn't. Okay, so that's the first family, and now we move to data science. Well, first of all, in data science, we are going to derive exploratory queries. So we are going to explore the data collection and the partial results within a process that will lead to a result. And this exploratory process is related to analytics operations. You probably will see that analytics is not part of the official dictionary of English, but in the discipline, in order to make the difference with analysis, which is most of the times related to data warehousing, people use analytics to refer to the use of machine learning and statistics, etc., models in order to explore the data collections. And so you are seeking for models or classification models or prediction models. The execution model is step by step. It's not that I write my query, I send it to the server, and I have my answer. It's that the query will be executed in steps, like a workflow, and each step will provide me with results, and with respect to such results, I will decide which will be the next step to ask, etc., until I get a result. The results are always approximative, and they always have a degree error that the one that implements the solution must estimate. Okay, it is always a degree of error, and there is also a possibility of to define scores that estimate how close your result is from an expected ideal. This changes completely what we have seen in classic query. And the data that feed this step-by-step process is extension and normally raw. And sometimes with a high degree of variety. It looks like this query, data science query. In fact, this is the generic workflow that normally people implement. It's like a schema of strategy that people implement in order to address these new types of queries. There are 4 groups of actions that have to be done. The first action is to explore and prepare the data that come in rawness, a high degree of rawness. The second group is applying models, mathematical or artificial intelligence models, in order to drive some conclusions. In between, in the data exploration and preparation, you will have a lot of visualization phases that will help those that can see to understand the results of the different phases. And when a second insight and foresight search, there will be a lot of assessment and ablative analysis with scores in order to estimate the validity of the results. And this thing is repetitive. I don't know to which point you applied machine learning models in artificial intelligence, but I suppose that you remember that for any model, what happened is that you have a lot of parameters, and so you apply the model and you saw the result, and then you modify the parameters, etc., until you were happy with the result, and happy with the result meant have good performance, and performance was estimated with respect to several scores, depending on the algorithm. Did you see such kind of thing? Did you?
Doctor, could you please repeat that last part because I didn't understand?
Yes, I want to know if in artificial intelligence when you applied the models that you learned, uh, if you remember that when we apply a model, an artificial intelligence model, we have to play a lot with parameters. So you play with some parameters, and then you evaluate performance, and performance is given by different scores depending on the model that you applied. And if you are not happy with that performance, you do a second try with new parameters until you get a good performance.
Yes, I think we did. Well, I don't know if it also counts, but like I remember that also on our uh, we took a course. I think it was last semester. That it was artificial vision. I don't know if that comes to
Yes. Mhm.
in which we did like face detection and hard plate detection, and there was also the playing with the parameters in order
Modeling.
to get better results.
Right. Okay. So this kind of process is this part. You prepare your data, you fragment your data, for example, for training. The model implies training. So you fragment your data in order to train your model, and you validate with respect to ablative analysis and error analysis. And then once you train, then you apply to the test data collection in order to really validate what you have done and you have obtained as model. So this would be this part. Okay, and so all together you have an instance of this strategy that will implement the process that will answer a query. Okay, here in data science is we are going to design processes with combining many different algorithms and strategies in order to answer a question. And you can have different tries, different algorithms with different variables, with different situations, and all this is why I have some boxes, because you have different instances of such process that run your solution in different conditions, and then all this leads to some results that will let you decide which is the best result possible that you can obtain, and that result is the answer to the query. So main differences with what we know, first of all, that you remember, because I also have said that normally in classic querying, you start with a mini world, and then the database represents the conditions of such mini world in any at some extent, depending on the strategy, but this is the case. Here, raw data represent observations of phenomena. and they are described as series of features or attributes. Okay, so it's like an Excel records of variables with values that represent variables, like that. Records. That's the kind of raw data that we have at the beginning. Now, the query has analytics objectives, so it looks for insights or foresights, and it is expressed as a pipeline of operations guided by the conditions and the characteristics of the data. This means that if there is a new collection, even if the query is similar, if you have a new collection of data, you have to design again the whole experiment. And the result is a model or a prediction with associated assessment indexes. It is never definitively accepted, and there is always an error, a margin of error, and it is accepted by comparison. So this is why I'm telling you that for one question, you design several possibilities of solution. These are the implementations of your query, and then you compare your results and you choose the one that produces the best result possible with respect to a set of performance criteria. Example of this, consider that we have an IoT example where you have a house, an intelligent house with many different sensors that produces spatiotemporal series with variables, whether you observe internally the house, for example, electric consumption, indoor temperature, indoor humidity, gas consumption, and then the outdoor temperature and humidity that have an impact on it, and you also consider meteorological variables like precipitation, clouds, etc. And you want to, the question you want to answer is, does it make sense to invest in low carbon technologies? Do I buy or not? Do I modify my house such that I will get a return of investment in my energy consumption invoice? So a pipeline in order to answer such a question would look in general aspects like this. So you can consider that the house and meteorological data provided by many sensors. You have at the starting of the pipeline to feed it, and then you have to perform data preparation, because here you have a lot of variety, different granularities, for example, different representations of the variables. You have to prepare your data here, and then eventually you will have to perform and apply on it some models that would determine the amount of energy consumed out of the observations obtained. Then you would, for example, estimate the CO2 footprint, and with this together, you could then drive a prediction energy consumption and CO2 footprint in order to decide what is the behavior of the house, um, and then whether it would make sense to invest. And then if you zoom into the matter, well, here you could apply many different, you see statistical distribution, observations, identification of outliers using many different techniques in order to understand your raw data. Then, for example, you would have to, in order to estimate the consumption of the energy and understand how this energy is consumed across the year, along the year. You would have to apply different algorithms in order to understand this and see how precise this estimation is done. Then you do the same on the CO2 formula estimation, for example, identify which are the variables that really impact CO2 footprint, for example. And then at some point, you would observe that, for example, during winter, you have a specific type of consumption, then, and in summer too, and so you would say that what out of the observation, it would be interesting to invest because you would reduce CO2 and energy in Christmas and summer, the the moments in which you consume the most, for example. So you see, it's driving this set of operations in order to have the conclusion out of the data that we obtain. Then we change to Mexico, or we change to Cholula, and then suddenly maybe other this would drive to other conclusions, particularly because, for example, in winter people do not have vacations and go skiing, so they are at their houses, and so they have different consumption profiles. Or because in summer, particularly in Cholula, it's not that hot, so the consumption does not vary enormously. So you see, for the same question, but changing only the input data, your pipeline would completely be modified. And okay, so you have understood that the first big challenge is to understand the pipeline. But what happens if we have the pipeline already? How do we implement it? And this is what we are going to start. I hope that today or next time. I think that today we still have some possibility. So there are many data science toolboxes today that help you implement your pipelines at different scales. Most of them rely on cloud solutions because, well, even if we start the lab in small scales, it is always much more simpler to use such kind of solutions in order to drive the pipeline. So that's something that I'm not going to repeat because we have repeated a lot, the general architecture, so different services to be used. And normally today we will see that they are packaged together. Okay, so providers provide you the right packages with all the tools necessary in order, for example, to do data science. Okay, so there's no need that you configure your own cloud solution. They already provide you with some ready-to-use solution. So today you can find three different, again, families of solutions that go. In the left side, you have most technical toolboxes. So this is for engineers, okay, not for people, non-engineering computer science people that would like to develop some experiments. So you have what we call big data platforms and stacks. They are based on the reference architecture of the cloud. Here you have much more layers. You have, of course, the infrastructure, but you have these for storage, you have platform as a service, data as a service, function as a service that we will see almost at the end of the course, and then software as a service. So a huge stack with already a lot of tools that are necessary in order to develop this pipeline. And so you have these ready-to-use stacks that are available and that makes your life easy in order to run experiments. The other type of solution, the one that, for example, Microsoft and Google and other cloud providers do, is having virtual machines specialized for data science. They are in general independent of the operating system, and you have everything you need in order to run your experiment. So that's the very technical thing. Then you have the first step solution, where you start exploring the problem or the query. You start sketching the solution with a controlled environment and they are reduced, and I don't one that we use, for example, in Colab as an example. So they are IDEs running on the web with all necessary tools and resources in order to run experiments. And then that this at the end of this lab, we'll see just by the end of the semester, there are also machine learning services that want to solve something that we will see while we will develop such solutions, that is a data management divide between what you do in your experiment and the way the data management works. And normally this has to be solved by a lot of engineering effort. And the idea is that these machine learning services reduce this divide, and they also provide mechanisms in order to deploy the solutions and really maintain them, I mean, at scale in real conditions. So you need a lot of monitoring, a lot of evaluation, a lot of performance of your processes, like in industry, in the chemical industry, etc. People observe the processes and how machines run, etc. So these machine learning services provide this kind of tools when you are really on their deployment and maintenance phase of such kind of queries. I always animate this and I forget to animate what's supposed to do this. I leave that. Okay, so we are going to start working in the middle, okay, like we did in lab. Normally, two things that we have to consider is which programming language we are using in order to drive our experiments, and what are the tools, the libraries that this programming language proposes, so that we have our life easier. So just to tell you that there are like two schools. The school that comes from people, programmers and people, programming engineers that use Python in order to implement these pipelines. And there is the other school from engineering, like electronic engineers, mechatronics, this type of disciplines that are quite used to MATLAB and to a language called R. Okay, so I think that I've seen that in Atus Lab, there is publicity about the seminars and other kinds of courses, tutorials on R. This is because this community, and then sometimes communities like social sciences and humanities that apply this kind of methods tend to use this R language. Okay, so we are using Python. In Python and as in the other approaches, there are already 5 libraries that support with almost all classic algorithms that can be used in order to address data science questions. Okay? Of course, there are other questions that cannot be done with these, but a lot of them can. So these libraries deal with multidimensional arrays. So the first one is NumPy. There are many problems that are solved with linear algebra. Matrices, and normally you apply a lot of linear algebra operations in order to work with your data. And in order to, well, that you have done at the beginning of your studies, we have to learn how to program, how to deal with matrices, but then we discovered that in fact many languages already provide you with libraries that help you do that instead of programming. We will have to know that, but others don't. So NumPy provides already with the necessary libraries in order to apply these linear algebra functions on multidimensional arrays, which are matrices. Then there is SciPy, that again, that in numerical algorithms you have seen that many problems in engineering, for example, are solved by numerical algorithms. And again, this library provides you with the most common numerical algorithms in order to deal with problems. They include signal processing, for example, optimization, statistics, so all the engineering mathematical background that we all learned as in the engineering school, and that is used in different engineering disciplines in order to solve problems. So that you have. This is to say that those that thought that the common core of engineering was not useful in computer science, you are wrong. It serves. So then there is a lot of visualization. So the classic library, it's a horrible library because it produces very ugly graphics and plots, but there are others, but well, the basic one is matplotlib. And then you have machine learning, and in machine learning and in general artificial intelligence, because there are also neural networks, etc., you have scikit-learn that provides you with everything you need for applying machine learning and artificial intelligence. And then many observations come in tabular form. And so there is a library called Pandas that helps you deal with tabular representations, and which makes it possible, particularly in the first part, which is data exploration and data cleaning. The first approach that we do in order to start understanding the data collection, if the data is tabular, Pandas is a very interesting tool to start. And then, well, there are two possibilities. I'm not going to introduce IDEs because you are used to IDEs. So there is a very popular IDE. It's not the only one, but a very popular one, which we started to use in the other lab. It's Jupyter. So we are going to use Jupyter, and normally, in order to use Python, if you install it locally, there is Anaconda that provides you with all the toolboxes and everything necessary in order to play with Python. But since we are working in an externalized manner, this is provided by the cloud, and we do not have to consider that. But anyway, it's good that you know that this Anaconda is the one that contains all the toolboxes in order to deal with Python if you are not on the cloud. And well, and more than that, we will go to the browser to deal with Jupyter, and more than that, we will delegate it to the cloud. So this is where the cloud has its importance, because if you have to deal with the installation of the environment, etc., the maintenance, the libraries, and then developing the pipeline, which is already difficult, then there is too much to do. So it's better to have a ready-to-use environment, and then you care about answering the queries. So that you know, because we have already seen this. So these are notebooks that are interesting to do. Now, particularly when you are starting to address a problem, because these notebooks can be shared. You saw in the previous exercise that you can share your notebooks, and someone can run the notebook. And then it's easy to communicate, and you have also all the log of your experiment with all the decisions that you make regarding your experiment. So you have at the end the result, the decisions that you made, why you used a certain function, the parameters, etc. And so you have everything in an auto-contained document that you can even export on HTML and on your site. Now, what we are going to do is the following. I'm going to show you another solution, a very general solution, in order to deal with these experiments, called Kaggle. This is why I asked you to create an account. What we are going to do in this lab is, again, me and my group, we have prepared all the necessary in order to run several experiments, and they are lying on GitHub, so that you know we use it as a store. And we will communicate GitHub with Google. And again, we will, this time instead of Colab, we are going to use Kaggle, which contains the interpreter of Python, the file system where you will have what you get from here to here, the notebooks. The notebooks you are going to did I lose connection? Oh no, okay. Sorry, I thought I'm like putting bandwidth today, so I thought I had lost connection. Okay, so you have this, but this time we are using Kaggle, and then of course the browser, because we have seen that it's the entry point to all this. Now, we are going to start having a look at, Kaggle has two parts, two perspectives. It has a data lab and it has a running experiment lab, okay? The data lab is where we and the world shares data collections of many different types, okay? So Kaggle is not the only one that provides a data lab. There is, of course, Google Colab that has a data lab, and there is Azure also that has a data lab. Normally, a data lab looks like this. You can have your data either lying on a cloud storage solution or on your disk, or the disks of your organization. On top of it, you have file systems, and in fact, you have distributed file systems that give access, transparent access to this data. Then you can have NoSQL databases that can access to this, and you can have data processing tools that can also observe this and do things as we will see, analytics things. And then you can have on the top tools in order to label your data collections and then version your data collections. The principle here is that there is a set of observations, and the one that collects these observations does a release. And then the work continues and more observations are produced, and then you have a second release, etc., etc. So people produce releases of observed data at in different periods of times. Okay, I don't know if you're acquainted with Stack Overflow. I suppose you do. For example, Stack Overflow exports releases of the interaction that people have there at different moments and of different sizes, so that if we do not have a lot of resources, we can get a release of all the interactions that are produced within Stack Overflow, and so you can play with them. Okay, so that's the principle. So let's have a look at least, oh yes, we still have some time, okay, to this. You do know Stack Overflow, no? You do or you don't? Yes, okay. Okay, so in order to play, we are going first to do the first thing that I showed, which is getting all the material that we have in GitHub into, well, all the material, all the data into Kaggle. Okay, so I'm going to first give you an overview of Kaggle for those that do not know Kaggle. So Kaggle looks like this. It has many different services. As I said, those that are the most important ones, even if I will explain in a minute that others too, is the data sets, which is the data lab where people share data collections, and the code, which is the space where we have notebooks and we run the notebooks, and people can also share to the world the notebooks. Okay. Now, it works as a social network. It's more or less like Stack Overflow. So you get reputation. Here, the reputation is poor because I created one account for the course. But anyway, you acquire reputation because Kaggle is an organization that proposes competitions for data science. Here, for example, we have one. The H&M Group has launched a competition in order to provide solutions to do personalized fashion recommendations. So companies share their data and propose a problem, okay, to the world. And competition means that you inscribe and you pay more or less not that much, but there is an economic price behind. Okay, so you have a month or a week, or normally it's a month. You see here you can earn $50K if you win. So they propose the problem. You inscribe. You can be alone or in a team. They provide you with the description of the problem, the type of questions that you have to answer, and the way you have to deliver them. Normally, it's not in the form of notebooks, and so teams develop their solutions, and they are evaluated, and the one that wins money. Okay, so many different, in particular American universities and other particular, I mean, freelancers, for example, earn money like that. And so in many universities in the States, there are coaches, professors coaching the teams, and the university, for example, pays the inscription, and then the coach provides you with knowledge about algorithm strategies, programming strategies, etc., so that you go for the problem and you try to win. And it's also, of course, a reputation. So every time you address a problem, and depending on how you are graded, you acquire reputation. And this is how you acquire this like that. Or there are courses. So if you, in a personal project, you are interested in developing data science skills, there are very good courses provided by Kaggle where you can get acquainted in more detail to data science. Okay, so you have this, and but we are going to the data sets space. So when you land to the data set space, so the data lab, as you can see, there are data sets of anything you want. And so it provides a search engine. Data sets are normally, we'll see in a minute, data sets are tagged with topics, etc. So any data set that you can imagine, you can see here. For example, let's use this one. So normally when you land into a data set, you know the person that provided the data set. For example, here it is the second version, that there are two versions of the data set. It describes where the topic and the content of the data set, and when it was updated. For example, this one 2 hours ago. Once you upload the data, the system automatically does a first processing of your data. And something that it estimates is the usability of your data collection. The usability depends how much metadata and how much description of the data you provide, so that someone that wishes to use this data collection can easily approach to it. Of course, we always say, okay, data collections are there, they are democratized, but they have an owner. So data collections have different types of licenses in order to determine the conditions in which you can use them. Then this data collection is nice because it is tagged, so the provider will use tags in order to describe the content of the data. You have to, if you want to have a good usability, you can provide information about the provenance of the data, the source of the data, the organization. You can describe the conditions in which your data was collected. And then you land to a technical description of the data. You have, for example, in this data, it weighs 11 kbytes, so very little. It is provided in two files. One is a CSV file, so a tabular file that weighs 8,65 kbytes. And there is a second file, which is a text file that weighs to 22 kbytes. You have also the description of the file. Okay. Here, since the file is, well, maybe this one. Yes. When you have CSVs, the system automatically generates a set of statistics of the content, quantitative description of the content of the data. For example, this CSV has these attributes. Here we will see. So it has 5 integer columns and 1 column of type string. Okay. Here is the distribution of the values of the data. It also provides you, well, here you can explore, and it also provides you, if there are null values or missing values, it also estimates the number, the percentage of missing values that you have in per attribute. Okay, so that quantitatively you can see, you can estimate the quality, the completeness of the data. So you can have it in detail. It can provide you a compact without the plots, or per column. And you see here you have valid data, you have a lot. There are mismatched data, missing data, the mean value of all the values of this attribute, standard deviation, the quantities, etc. Okay, so for every column you have this very detailed quantitative description of your data. And then you can also see in code the analytics that have been performed on this data collection. For example, here there is only one notebook implementing some analytics on this data collection. If many people are using it, for example, here there is no discussion, but you can discuss with many if they are using the data collection for doing some analytics. It describes the views, so how many views, how many downloads, etc. So the activity that it generates, and then the metadata that it has. You have usage information, particularly the license, whether it is visible. It's public because we are having a look at it. The provenance, so here you have the link to the provenance, who maintains the data, and the frequency. When you generate many versions, it computes the frequency, or you can declare the frequency in which you are going to maintain your data and generate new versions. Right? Nice, no? Okay, so now we are going to generate one of our own. And in order to do that, well, first of all, do you have questions? Because I'm talking and okay, so let's move to the first part of the data lab. I think that the first thing that we will manage to do is just create a data collection of our own. So if you go to the course, I'm going to put the link on the chat. So you have the link there. If you click on environment, you will land to this little space. So I put a PDF with a Python memento. You will see. Well, I don't know if you program in Python, but I mean it's nothing extraordinary to be done. So there is a memento if you need, but you'll see that if you haven't already programmed in Python. So now we're going to prepare our environment. So we are going to create a data collection that we will use in order to implement pipelines. Okay. So if you click on here, you have instructions. Maybe the screenshots do not really correspond to the new version of Kaggle, but I mean, there's no particular thing to do. So you go to Kaggle, so you keep that. We will be going back and forth. So the first thing is that we are going to create a new data set. And then here in the data set, we are going to, we have to name it. So I'm going to name it. You can name it as you want. If you see here, you can your data set can come from your local machine. It can come from a URL. It can come from GitHub, from another file, or from the cloud. So we are going to use GitHub in order to upload our data collections, because we are using a lot. So in GitHub, well, blah, blah, you are going, it has become much more simpler than before. You are going to copy this address in order to so when you copy the address, it connects, of course, to GitHub, and then you have, well, it says 0 files because we have an organization of files, so it cannot process all the tree, but there are data you will see. Okay, until here, right? And then you create. So we're happy it has been created, and we land here. So I have the name of my database. My user name is this one. You will have yours. It has been updated just now, and it's the first version. Then we can fill in. I will let you fill in your metadata, because for the time being, since it is There is almost no metadata. The usability, you see, is very poor. So the only thing that it's good from the point of view of the system is that we are using well-known file formats. Okay, if we have formats that are weird, so we wouldn't have even this checked. But well, it considers that the formats are right. So here, for the time being, the data collection is private, but we can make it public. We could add tags to it, so that you will do later on. And here we can explore its content. So you see we have many different folders, and in each folder we have CSVs in this case. In this folder we have an unknown and .data format. Here we have CSVs, etc. Okay, here we have a lot of files. And then here again just a CSV. Okay, so that's what we have retrieved from GitHub. And for example, if I click here again, I will have to see the different attributes that it is composed of, um, how many unique values, here 32, here 1, etc. Okay, the distribution you see here, for example, in time, there is a lot of 2000, then more or less even, and then in 2011 there are also a lot of data, a lot of entries with that value. So we have a summary, it has 25 files and 139 columns. And if we wanted to upload a new version, we could. Right? So I think that, I mean, it's not that rocket science or anything. You have the description here, as you have seen. Well, at the time that we created the reference, it was much more complex. Today, it's just 2 clicks and you are there and you have your data collection ready. So we do not have time today, but next time we are going to do 2 things. First of all, getting acquainted with the system, and particularly with the code lab. We are going to play with pandas, with the first exercise that you can get acquainted, but pandas with a query already, a data science query that we have to solve through a pipeline, just applying statistics. Okay, and only with statistics that this will drive to a certain result that can be used in order to answer that query. And we are also going to use descriptive analytics that time in order to really start addressing other types of questions. So these are the 2 examples that will let us step into the real challenge that we are going to address here, because you are computer scientists and engineers. Then we will go through a parallelization, etc., versions, etc. But it's just to get you acquainted and see how it works, how it looks like, how do experiments look like, and then really go to much more challenging exercises that will deal with parallelization and other things. Okay, so I'm going to stop here. Of course, if you have questions, it is the moment. And otherwise, I'll see you on Friday. Yes, one thing. Today I uploaded the use case for the course. So now you have the use case and you have, I think, everything ready to work and hand in things on the 20th February. And I don't know, I think it's Francisco that was worried about the calendar. Now I think that the calendar is up to date with the right deadlines.
Yes, yes, now it's updated. Thank you so much, Doctor. Have a nice
Very good. And of course, have a look at the use case. And if you have questions, any question, remember that it's not like an exam that I give you and that you answer and I grade. The idea is that you work on it, and if you have questions, you can interact with me and ask and tell me, I don't know, I'm planning to do this, is this right, etc. And I can give feedback. Okay, it's not like scholar example, I give you something and then I grade it. It's by construction that you have to work. Okay, dear students, so we are going to stop here and I'm going to stop recording. Now I recorded. Thank you for